Hey everyone, and welcome back to the podcast. Mark here with Jenny.
Hey everyone.
Today, we are diving deep into something fundamental to nearly every piece of tech you touch. The memory that makes it all hum, especially that super fast kind, but it's hitting some snags as we shrink things down.
Exactly. We're talking about SRAM, or Static Random Access Memory. Think of it as that incredibly quick scratch pad, right on your computer's processor, that keeps things moving at lightning speed. It's been a workhorse for decades, doing its job quietly, but it's facing some real hurdles as chips get smaller and smaller. So Mark, for anyone maybe not steeped in chip architecture, what exactly is SRAM and why is it such a big deal?
Oh man, okay, think of your CPU like the brilliant professor in a library. He's doing intense research, right? He needs reference books times instantly. SRAM is the tiny, super organized desk right next to him, holding just the few books he needs, times right now. It's designed for extreme speed, sitting right on the same chip as the processor. Unlike your hard drive, if you turn the power off, it forgets everything. But for those quick calculations, that immediate data access, it is king.
Right, speed is definitely the name of the game with SRAM. That immediate access. But I've been hearing that as we try to shrink things down to these incredibly tiny sizes, we're talking like the scale of a few dozen atoms, 20 nanometers and below, we start running into significant problems. What happens at that minuscule level?
Here's where it gets, a bit mind-bendy. When you get that small, the everyday physics we're used to starts giving way to quantum mechanics. The components inside an SRAM cell, tiny transistors and wires, get so close together that electrons, those little charge carriers, can start doing something called quantum tunneling. They can, for lack of a better word, jump through time's barriers they shouldn't be able to. This messes with the stability of the memory cell, potentially causing errors, flipping a 1 to a 0, or vice versa.
Okay, wait, let me wrap my head around this. So even though there's a physical barrier, like a tiny wall, the electrons are just phasing through it? That sounds wild. Like something from, I don't know, a sci-fi movie about nanoscale intruders?
It genuinely does, doesn't it? But it's a very real phenomenon at these scales. And the smaller you make the SRAM cell, the thinner those barriers become, making this tunneling effect more likely. This directly impacts how reliable the memory is, and also increases the power needed to simply keep the cell in a stable state. It's a genuine puzzle box for chip designers.
So it's kind of like trying to build an incredibly tiny, complex structure, but the fundamental building blocks are becoming leaky? How do chip manufacturers even cope with this? Are they just stuck at a certain size?
Well, that's where the story gets interesting. There's been a common narrative that SRAM scaling is sort of hitting a wall, or is dead, at these smaller nodes below, say, 5 or 7 nanometers. But then you see companies like TSMC, a giant in chip fabrication, constantly pushing the boundaries. Their newest process, the 2 nanometer, or N2, is actually showing some promising, measurable improvements specifically for SRAM 2-3. It seems the rumors of SRAM's demise might be a bit premature.
That is fascinating. So they're finding ways to work around or mitigate these physical limits? What kinds of improvements are we seeing with TSMC's 2 nanometers process? Is it a small step or something more significant?
They're reporting noticeable gains that are definitely not insignificant. We're seeing improvements in density, which means they can pack more SRAM into the same amount of silicon area. We're talking something in the realm of 38 megabits per square millimeter, megabit per square millimeter, at N2-3. And crucially, they're also getting performance increases and reductions in power consumption. Reports suggest things like around 18% performance improvement and significant power reduction compared to their previous nodes, like N3, E2-3. So they are making progress on those key metrics.
Okay, those sound like solid steps forward. Better speed, less power, more memory in the same space. But is that pace of improvement enough to keep up with the increasing demand for speed and, especially, for bigger chunks of memory? In areas like AI and machine learning, it feels like the hunger for more cache, more nearby memory, is growing exponentially.
That's the central question that the industry is grappling with, isn't it? While these 2 nanometers gains are genuinely good, Some experts and analysis suggest that the percentage of scaling, how much smaller and better the SRAM cell gets with each new process node, might be less pronounced below N3 compared to, say, the logic transistors that do the actual computation, which are still improving faster. 1. So, the improvement in SRAM density isn't necessarily keeping pace with the improvements in the processing power that uses times that memory.
Okay. So, the traditional approach of just making the SRAM cell itself smaller and smaller isn't scaling at the same rate as the processing part of the chip. What implications does that have for how sophisticated chips are designed these days?
It's prompting a pretty significant strategic shift in the industry's approach to chip design. Instead of simply trying to cram massive amounts of SRAM onto the same physical piece of silicon as the main processor, companies are increasingly looking at what's called heterogeneous architectures, or cache tiering. 4. It means they're using less of that prime, on-chip SRAM real estate for only the absolutely critical, speed-sensitive data, and relying more on advanced, oftentimes off-chip times memory solutions for larger amounts of data.
Okay, cache tiering. So it's like having different levels or types of memory, each optimized for a different purpose and speed requirement? What kind of off-chip memory solutions are we talking about then?
Exactly. Think of it like having different levels of storage importance. You're seeing major players like AMD and Xilinx implementing this. They'll use that very fast embedded SRAM, often called L1, L2, or L3 cache, right on the processor die for data that needs sub-nanosecond access times. But for larger data sets, things that are used frequently but perhaps not times every single clock cycle, they're leveraging technologies like high bandwidth memory, or HBM. HBM sits off-chip, but often stacked vertically and placed very close to the processor using advanced packaging techniques. 1.
HBM is that stacked memory you see on high-end graphics cards and AI accelerators, right? It's known for its extremely high data throughput. You can get massive amounts of data in and out, but, as you mentioned, the access time, the latency, is longer than SRAM, that's actually times on the chip.
Precisely. We're talking access times potentially in the range of 150 nanoseconds for HBM compared to maybe 1 nanosecond for that fastest on-chip SRAM 4. So yes, there's a latency penalty there. But by intelligently optimizing the memory hierarchy, figuring out what data absolutely must have that immediate on-chip access versus what can tolerate a slightly longer trip from off-chip memory, designers can still significantly improve overall system performance. And, very importantly, they save that incredibly valuable and expensive space on the main processor die.
Saving die space seems like a pretty massive motivator, especially considering how incredibly expensive manufacturing at these advanced nodes like 2 nanometers is. I read somewhere that this approach of using less on-die SRAM and moving to tiered memory can reduce the die area consumption by maybe 20% or even more compared to trying to cram all that necessary SRAM onto the main chip.
4.
That must have a big impact on the final cost of the chip.
It makes a considerable difference. SRAM is notoriously dense in terms of the die area it requires, and at these bleeding-edge nodes, that area translates directly and significantly into manufacturing cost. So while the efforts to continue shrinking the SRAM cell size are still absolutely happening, thanks to the innovation at companies like TSMC with their N2 process, the economics and the fundamental physics are really pushing the industry strongly towards these layered, tiered memory solutions and advanced packaging approaches.
Okay, so it's a multi-pronged approach. Beyond HBM and the ongoing SRAM scaling, are there other emerging memory technologies on the horizon that might eventually complement or even potentially replace some of the roles currently filled by SRAM? I've heard whispers about things like MRAM, phase change memory.
Oh yeah. This is where the future landscape of memory gets genuinely exciting and complex. MRAM, or magnetoresistive RAM, is definitely a technology to keep a close eye on. A key feature of MRAM is that it's non-volatile, meaning it retains its data even when the power is turned off, similar to how flash memory works. But critically, it has the potential to be much faster than flash, potentially approaching SRAM speeds for certain operations. This could make it attractive for certain types of cache or working memory that needs persistence.
Non-volatile and times fast? That honestly sounds like the holy grail of memory. The speed of SRAM with the data staying power of flash. So could we potentially see MRAM eventually taking over and replacing times the SRAM in a chip?
Not quite yet, or at least not in a wholesale replacement sense. While MRAM shows great promise in terms of speed and non-volatility, it still faces its own set of engineering challenges. Things like endurance, how many times you can reliably write data to a cell before it degrades, and the write speeds aren't always quite as fast or energy efficient as SRAM for every single application. There are also other emerging memory technologies being explored in labs and by startups, like FRAM, or ferroelectric RAM, and ReRAM, resistive RAM. These are all being actively researched and developed, but each one comes with its own specific trade-offs in terms of speed, density, endurance, and manufacturing complexity.
So it really sounds like we're not just searching for a single SRAM killer or a simple replacement, but rather the industry is moving towards a future with a diverse mix of memory technologies, each playing to its specific strengths and being used where it makes the most sense. Is that the vision for the future then? A big, complex, interconnected memory ecosystem?
That certainly seems to be the strongly indicated direction things are heading in. The future likely involves complex, hybrid memory architectures. These would combine scaled-down, optimized on-chip SRAM for the fastest requirements, potentially leveraging off-chip solutions like HBM for high bandwidth and larger capacity, and maybe incorporating some of these emerging non-volatile memories like MRAM for specific functions like persistent cache or configuration storage. All of this integration is becoming possible and practical due to advanced packaging techniques, whether it's chiplets, building a processor out of smaller specialized blocks, or 3D stacking, putting layers of different chip types on top of each other. It's about creating a highly customized, efficient memory solution tailored for each specific workload, whether that's a massive AI model or a high-performance server CPU.
And that advanced packaging allows you to put these different types of memory and the logic processors incredibly close together, even if they're not fabricated on the same piece of silicon all at once, right? Kind of bypassing or significantly reducing that penalty you get from having to send data a longer distance across a circuit board.
Precisely. It's like building a really advanced, optimized structure using different types of specialized bricks and connecting pathways extremely efficiently. It directly addresses and helps mitigate some of those latency challenges you inevitably encounter when data has to travel off the main processor die to external memory. It is a genuinely active and crucial area of research and development right now, how to seamlessly integrate all these different pieces.
So while the traditional path of simply making SRAM cells smaller, times getting much harder, and facing those fundamental physics hurdles, it's not a dead end. It's actually forcing this fascinating wave of innovation across the entire field of memory technology and overall chip architecture. It's not the death of memory scaling, but perhaps better described as a complex and diverse evolution into heterogeneous systems. That's pretty cool to think about.
It absolutely is pushing the industry to think in more sophisticated, systemic ways about memory. And look, it goes even deeper than just the components. You even have researchers and industry leaders, like Dr. Rachel Tate from GlobalFoundries, discussing how, as we continue to push towards smaller and smaller nodes, eventually down below angstrom scales, the challenges become so fundamental that we might even need things like radiation hardening and standard consumer chips to protect against transient errors, soft errors, caused by stray cosmic rays or alpha particles emitted from trace elements in the packaging. 1. That really shows the incredible level of detail and the complex challenges involved at this cutting edge.
Radiation hardening. Wow, that adds a whole other layer of complexity I hadn't even considered. It definitely sounds like the future of memory and chip design is going to be less about just making one thing smaller and faster, and much more about intelligently combining a bunch of different clever solutions and materials. Mark, as always, you managed to take a really complex, deeply technical topic and make it feel remarkably understandable. Thanks for breaking that down for us.
My pleasure, Jenny. It is an endlessly fascinating area, and it directly underpins how fast, powerful, and efficient all our digital devices can eventually become. We'll certainly keep a close eye on these developments because they are moving fast, and keep you listeners updated. Until next time.
Indeed. See you then. And thanks for listening, everyone.